Vamos ver se já está dentro do. Ai, gente, aqui tem que botar. Muito frio. Ah, não vou mexer em nada aqui, né? Não, vou falar com ele aqui. Olha, meu pai, como está aqui. Muito caldo. Ah, acho que hoje está certo. Ah, dá para escrever no chat. Ah, sim, se tu quiser me mandar, mas daí tu me faz um sinal.
Ah, não, no celular não, no computador.
Como eu não entendi?
Eu assisto no computador, né? Tem o chat ligadinho e te mando.
Não, tu quis... não, acho que não precisa. Eu acho que não vai ter pergunta. Eu tô até olhando aqui, ó. Quem tem dois assistindo, eu e tudo certo. Tá no YouTube?
Não, então.
Acho que não vai ter nada. Acho que isso vem sempre depois, sabe? Vamos ver. Ah, no Meet tá ali também. Ali no Meet só tá.
Aí eu acho mais fácil.
Cadê o Pedro? Eu vou desligar aqui, que isso aqui vai dar. Vai dar. Tá, eu vou só olhar no YouTube. Já perdi, né? Um espectador deve ser. Cadê o Pedro? Ai, faltou uma água, né, professor? Que tá lindo aí. Hã? Tá tudo certo, né? Só falta a pessoa, né? Só falta. Será que eu consigo fazer uma água pra ele?
also
Yeah.
they told me that most of the people are students. They have to be like
Yeah.
introduction. Okay.
Okay, it's good. Alja told me she couldn't, probably she won't be here because I think she had
Yeah, problem with
the dentist appointment, yeah? Yeah. Okay. Let me see.
yeah, he told me a lot. I had some animations, so that's why. And also yesterday in the night I did an image
Ah,
that I added. So,
um, this is the point.
Olá, muito gosto. Olá,
hola, Pedro.
I don't know what this is. But you can use. Yeah, if you want.
Because normally people say that
No, it's necessary to talk.
Right?
It is working? Yeah, okay.
I thought it would be right there. The letters they look different.
Yeah,
Can you read?
yes. Esse projetor tá ruim, né? Ele parece umas.
Ah, essa chuva, né?
Essa chuva, isso já teve
isso eu
no.
já notei.
Foi na vez passada, eu já notei que tinha.
É verdade. Tem que reclamar, né?
Vamos esperar um pouquinho mais, pessoal.
The background seems to be stars.
Yeah.
I don't know.
nosso palestrante é o Pedro Mili Rodrigues. Ele é o mais novo pós-doc do departamento do nosso departamento. Ele é do grupo de extragalactic, sob a supervisão da professora Cláudia Mendes. E ele fez a sua graduação e mestrado na Universidade de Concepción, uma instituição muito conceituada no Chile. Depois ele mudou-se para a Alemanha, para Bonn, onde ele concluiu o seu doutorado no Instituto Max Planck.
Thank you. Yeah, thanks for coming. As I'm Gila said, I am the group of Claudia, and I hope you can hear me. Yeah. Normally I have problems with the design. So any question, just ask me. I know you are mostly undergraduate students. So I did an introduction because everything I will talk about from my thesis is from radio wavelengths. So just to compare a bit, I did this couple of slides. Normally in the interstellar medium, the ISM, there are three main transition types. So we have electronic transitions, the vibrational transition, and rotational transition. So for typical conditions in the ISM, we have transition frequency in the UV range for electronic or optical, vibrational in the infrared, and rotational for the millimeter. It falls in the millimeter due to the energy. If we translate the energy to temperatures, you will see that in radio we mostly see the space, very cold space. This allows us to study, for example, recent star formation where the material is collapsing. So we need very low temperatures in order to collapse the clouds and not expel the gas before a star is produced, for example. So, for example, CO can emit at 5K and above, and methanol, that I will show you later, is at 20, 30K, very low subthermal emission. Just you to have an idea of how the molecules move or behave, here we have the rotational motion of water, for example, and here the vibrational motion. So normally the molecule receives enough energy to do the rotational motion, but also an exit of energy, but make it also produce vibrational motion. So normally what we see in radio is a combination of bending or stretching plus the rotational motion to see it in a very simplistic way. So in radio we normally talk about raw vibrational transitions. So now I will start with the two topics of my thesis. Main topics were about carbon and sulfur isotopologue ratios in the galactic center to study the chemistry of our galaxy, and the other topic was methanol, could be in LTE conditions, local thermodynamic equilibrium conditions, and also in out of LTE that we call, it will be quasi-thermal emission, but also mixed. And for that, I study methanol in external galaxies, normally starbursts, Barrett starbursts like NGC253 that you can see here, and we focus on the center of them or the central molecular zone. I will talk about central molecular zone just in the next slide. So here you have carbon monosulfide. That is the strongest line for sulfur in the ISM and very common in very dense regions. And methanol, that is here below, that it consists in a methyl group, that is CH3. Every white point here is hydrogen, carbon, and oxygen. So this is the hydroxyl group and the methyl group. And it can move separately, like a spin of these four atoms with respect to the others. And here you have a momentum map or velocity map of the center of this of NGC253 with some stellar winds that you can see here. So the first topic, carbon and sulfur. Carbon allows to trace the CNO cycle or burning. That is primarily produced by intermediate stars, let's say 1 or 2 or 3 solar masses, and the sulfur that is for massive stars. it is producing supernova type 2 or collapsing. And the difference between this we call main species, the normal, and the isotopes is that they can be produced by in a single star, or also will mostly need the previous creation of 12C, for example, for 13C, and 34S will need also a previous creation of 32S. So the increase, if this amount increases, it means that there was a previous star and previous reprocessing of the star. So as the universe becomes older, you will see an increment of the isotopes. That is, the contamination of the universe will increase, we will say. So if we do the rate, we will see that this rate, the 12C over 13C, will decrease as the 13C increases. So this part of the Milky Way, this is the distance to the galactic center. This ratio will decrease as the Milky Way becomes older. So the center of our galaxy is older according to this ratio, that the spiral arms, and this is an agreement with the common scenario of inside-out growth scenario for carbon. But what happens with sulfur, and this was the problem, the main idea.
How the age is determined through this rate?
Sorry?
How the age?
The age.
You just said that the galaxy, as the galaxy gets older,
Yeah.
the ratio decreases.
Oh yeah. Can I show the appendix? How can I go to?
No,
Well,
don't worry.
there is a relation between metallicity and age that I can show you later in the appendix.
Okay, good.
But yeah, it's not like the real age, but we know that in comparison that is older. At least that
Relative age.
the relative. Yeah. So, but with the sulfur, the problem as of 2020 was that sulfur, there was just 1 point. So to get the sulfur ratio, we need, using the double isotopologue method, we need the carbon ratio first, because normally double isotopologues are very difficult to find. But we can also use direct observation if we have the double isotopologue and do the ratio directly. But this line was never observed in the center of our galaxy before. So to study sulfur, I focus on Sagittarius B2 North and the 50 kilometer per second cloud that are better observed here with a peak of ammonia. And there is an infinite shape also observed by Molinari in 2011, but this hasn't been seen in the optical yet. So it's a theory. And here is a more another, like, if we will see the Milky Way from external, from outside, we will see the center of the Milky Way like here, and the other part also in infrared, in near and far infrared, and centimeter wavelengths, we will see something like that, with Sagittarius B2 here, and the 50 kilometer per second cloud here. So they are at 130 parsecs from the center, and very few parsecs from the Sagittarius B2, Sagittarius star. So this is what we call the central molecular zone of a galaxy. That is a region with high density and strong kinematics. So line width, very higher line width. About the methanol, we have the formation of methanol. Just to give an introduction, methanol is formed in the ice mantles of dust. For example, here you can have dust and ice, and methanol is formed there by the dust will capture hydrogen until produce methanol, and the destruction, the most common, is due to photoionization or cosmic rays. But the photons induced by cosmic rays that will destroy the methanol and produce, for example, CH3 plus OH. Once the methanol is produced in the ice, then closer to the young stellar object, for example, it will sublimate and goes to the gas. and then we can observe it. But if this is very close to the star, it will be destroyed. So here you can see also other molecules at different temperatures. Methanol, mostly all the molecules are sublimated at about 150 or 200 Kelvin from the star. So methanol is a complex organic molecule. It has plenty of lines, more than 700 lines detected in this millimeter and sub-millimeter. For my study, I created, for example, this synthetic spectra showing several lines, and I detected around 150 lines. It is due to the complexity here. For example, this methyl group can proteins related to the OH. And for example, if one of the hydrogens here has an opposite spin, it will be methanol E. But if all the spins here are in the same direction, this will be methanol A. So it's divided into species or sub-species. These species can be also have different frequencies, different temperatures, and densities, and critical densities, as I will show you later. So this was methanol in LTE that can serve to trace dense regions, also weak shocks, infrared radiation, and if you are able to observe vibrational transitions, it will also trace kinetic temperatures. So at higher kinetic temperatures or gas temperatures, we will detect them. On the other side, for methanol maser, the maser phenomenon is like a laser but in microwaves. For this, you need a metastable state that can be produced by a spontaneous emission by the Einstein coefficient, and you will need a star or shock to move this metastable state to the ground state. It produces a cascade because if you think this circles as a methanol molecule in a metastable state, once a photon collides with it, it will go to the ground state, like here, and produce an extra energy, and this difference of energy, exactly the same of the frequency of the photon, will produce another photon of the same frequency, so exactly monochromatic emission, and then again, and it will produce a cascade. That means that as the photon, as the light passes through the medium, the emission will increase, and that we can say in physical terms as a negative opacity. We need more, and also since we need all the distance, this emission to be coherent or around the same velocity, the maser effect is more observable or preferably observable in the plane of the sky. So if you have a jet or a wing on the line of sight, you will not see that emission. But if you see if the outflow is in the plane of the sky, yeah, you will see that more or less the velocity of the systemic velocity of the source. So maser can be used to determine distance and velocities of sources, even in the extragalactic media, for example, with water masers. But here, continue with the methanol masers. They are divided in two types: class 1, originally pumped, and class 2, pumped by infrared radiation. Class 1 can also be detected in low mass stars, while class 2 are so far only detected in high mass star forming region. And they have more than 90% of correspondence with the continuum, gas continuum. That is an indicator of the star forming regions. So this line at 6.7 GHz is a good tracer for recent star formation. And here you have different frequencies for the class 1. The transition can also be seen here in the population diagrams. So here you have the energy of the transition, and here the K, that is the projection of the molecule on its main axis. So, for example, and these are the atomic transition from, for example, from 7 to 6. We haven't detected it, but all the others, yes. this we call like family series, all this. For example, for 9 to 8, we have detected it at 278 GHz, but nothing above it or in between at 181. The main difficulty to observe this line is the proximity to the water telluric line at 183 GHz. So now, how the object I studied to measure more transitions was NGC253. That is a nearby galaxy, starburst. It has a star formation rate of 1.67 solar masses per year, and a large and inner bar that are more or less a 90 degrees difference. So here you have the large scale bar, and also an inner bar that is here, about 90 degrees difference. Also in the X-rays, we have seen a stellar outflow here, perpendicular to the plane of the galaxy. And to give a context with the galactic center, a comparison, we will see this scale is about the galactic center, and that is what we call the central molecular zone. So coming back to the first topic, the sulfur. Here you can see sulfur and carbon on Earth. And for this study, I use the Apex telescope, the ALMA, and the IRAM 30-meter telescope. So what was known about sulfur before was this trend by G. And here is the solar metallicity. So we might think that the sun is older in comparison with the gross ISM. Yeah, what else? No relation with other isotopologues like 33S or 34S. Yeah, we studied the 50 km per second cloud that is here, and we observed this line for the first time, the 30C, 34S, that allow us to obtain the ratio directly. So I use this line and divide the other to get the ratio in column density and also the line ratio itself, and also the double isotopologue method using the carbon ratio and get the similar results. So this was for the 50 km per second cloud, and also for Sagittarius B2 we studied the continuum at 85 GHz, and mainly 4 points here, where the continuum peaks. This data come from the thesis of David Tien that were not published at that date. So from the velocities of the absorption lines in Sagittarius B2, we can determine the distance. For example, in Sagittarius A, we know that the velocities are between 5 and 22 km per second, and also negative velocities at 3 kiloparsecs, and also between -50 and -10 kiloparsecs at 1 kiloparsec from the center, the galactic center. So here, for example, we know our emission comes from the 1 kiloparsec disk, and also from the envelope of Sagittarius B2. So with this, we have already 3 data points from the center, and we obtain also the ratios that are here for the sulfur and for carbon. These are only the coordinates of the 3 continuum peaks, of the 4 continuum peaks I am showing you here. And this is a LTE synthetic spectrum for the absorptions. Also, we check for sulfur fractionation, that is the amount of sulfur that is really in carbon monosulfide and is not in other molecules. When we do the rate between carbon monosulfide, we will expect this is the real 32, 34S. But what will happen if most of the sulfur go to another molecule like H2S, for example? We need to know that, and for that we did the modeling. And for typical temperatures and conditions for the objects we are observing, for example, Sagittarius B2 is considered a mini starburst in our galaxy. So these are the 3 data points. the galactic clouds, line of sight clouds towards Sagittarius B2 that could be at 1 kiloparsec from the center. The 50 kilometer per second cloud that is about plus minus 3 kiloparsecs from the center, and the envelope of Sagittarius B2. So with this, we can put it in context with the previous observations of sulfur ratios at different carbon ratios, and we know that now we know that the trend is stopped at somewhere in between 0 and 3 kiloparsecs from the center. What could be the reason for that? Because carbon, nitrogen, and oxygen, all of them follow a trend until the center. The difference will be that the sulfur comes from massive stars at more massive than 8 solar masses, and also that the kinematics of the bar of our galaxy that has an edge of in about 4 kiloparsecs moves the material to the center. So this part, this metallicity here, will be similar to the center. And here the bar will also produce a disturbed medium that impedes the production of massive stars. That could be the idea. The second topic on methanol was also divided in two topics. One, look for methanol masers in more galaxies that currently known beyond the local group, and the other is also look for methanol masers but at higher transitions that known before. And for this we use ALMA. For the first study we use the Effelsberg telescope. It's about 100 meter telescope at 36 gigahertz. So in the context, previous to my thesis, what was known that was that for the Andromeda galaxy, the Large Magellanic Cloud, Mafic 2, IC342, and other galaxies, only some masers were detected, but never, for example, in Mafic 2. This in the Large Magellanic Cloud was detected in the 90s by Sinclair in class 2 metal lines, metal masers, M31. Also in class 2, that is the brightest in the galaxy, and for the first time beyond the local group by LXM, and then confirmed by the same group in GC253. While no class 2 metal masers have been detected beyond the local group. That is weird because in our galaxy, the brightest are the 6.7 gigahertz, but that seems to be not the case for extragalactic objects, or maybe the emission is just diluted inside our beams. So from the Effelsberg observations, we observed that in 2019, in February and January, we took the average and detected the line. But only because it's very strong, we can say that it's a maser. And it was later confirmed by Chen and others, by McCarthy as well, and also we determined non-detection in R220. And here is the confirmation of in Mafic 2 with BLA. This is the Effelsberg beam and the higher resolution with the BLA version. Also here, so what was known as of 2020 was all these transitions of metal masers in different galaxies, but nothing beyond 84 gigahertz, because normally people use ATCA or other telescopes like that are not cannot observe at higher frequencies, and no correlation with infrared radiation, so they are poor class 1 metal masers. So now the context also includes Mafic 2, and also we confirm in IC342 from a previous study of Worski, it was only once observed. But now the largest study was on metal maser in NGC253 using ALMA from the Alchemy large program. Alchemy observed ALMA bands 3 to 7 that cover between 84 and 373 gigahertz. And for this, we focus on 10 Gaia molecular clouds positions previously detected by the OI 2015, and we observed several molecules here. You can do a paper with any molecule, even with a single molecule. So this is the coverage as common angular resolution of 1.6 or 27 parsecs in linear resolution, and a spectral resolution of 10 kilometers per second. And for this, we use about 90 hours in the 12-meter array and 241 hours for the ALMA compact array. So we focus on the center of this galaxy, the 10 regions with the coordinates here. We have the spectra. And to detect methanol masers from all this, we need to compare with LTE lines, with the methanol that is in local thermodynamic equilibrium. And basically, to do that, we have two possibilities. Either do rotation diagrams or relative transfer models. The rotation diagrams come from mainly this equation. That is, you can think this like a slope equation with the slope, the x, the constant, and the y-axis. And for this case, the y-axis will be the logarithmic of the quantum density, that is like the density, the amount of gas over the atomic weight. And on the other hand, we have the slope, that is 1 over the temperatures, but in negative. So we will have a slope like that, not like that. And the constant will be where the slope crosses the y-axis, that is the total quantum density over the fraction, the partition function. So for the rotation diagrams, the problem is that we need only single lines, not blended lines. So I use all these methanol lines, the transitions, the frequency, and we also estimate some blending possibilities. And these are some of the, not the 10 regions, only 3 of them, but just to give you an example. So when you do this method, every transition of line, every line is 1 point here. And here you have all the methanol lines here, and the masers will be above that. If the line is opaque, and not maser, it will fall below. But if this is a maser or quasi-thermal emission, it will stay very high, very above the trend. For region 1 and region 8, we detected methanol masers, but for region 4, that is in the center of the galaxy, region 4 is about here, and region 1 is here, and region 8 is about here. So we detected some masers in some conditions. We also divided methanol in the 2 species, methanol E and A, and also here color-coded the critical densities that tell us from if the density to produce the line is, what is the density from which the line is coming from. So here I determine, for example, that low critical densities are better not fitted by methanol A, but they follow the slope of this one here. So here is the slope of the other rotation diagram. From the rotation diagrams, then we can obtain the quantum density, the amount of the gas, other than the temperature of the gas, of the excitation temperatures. So then what I did was to measure the distance from LT. So this line should be in this part, if this is in LT. So I measure the difference per region of all these transitions and got this. So this is the quantum density in the upper state of the maser related to the LT divided by the quantum density I will expect from LT conditions. And here you can see that it's over 3 sigma. While in the central regions of NGC is only LT. Also, since I detected methanol masers in these regions here, and also in the other part, I look for other conditions for methanol maser emission. For maser emission, like a quantum density below 6 times 10 to the 14 centimeters to the minus 2. Also coincides with the same regions where we see methanol masers. And temperatures for E methanol below 15K, also coincide, and a difference between temperatures between A and E. The difference in temperature, you can see, you can infer from the difference in slopes, since as I said, the slope of the rotation diagram is the 1 over the temperature. If we have a difference in temperature, we will see different slopes here, and a major emission when the slope is difference is high. So when the temperature difference is higher than 5 Kelvin, we also observe masers. Masers are also detected in different transitions, but for most of them, the strongest line was in region 7, up to 230 gigahertz, when the region 6 started to be the strongest line. Other relation I did was to measure shocks. Now, one way to trace shocks with molecules is to observe the SIO line. SIO is trace strong shocks, while HNCO trace mostly weak shocks. So if we do the rate between the two, here I only took the moment zero map of the two molecules. We will see that when we have a strongest presence of weak shocks, we don't see any masers, but when we have strong shocks, we have very strong lines. Also, the final thing I tried to do was to take those two transitions in LTE, take the average, and compare with the maser line and per spaxel. And if you do that, you will see a higher ratio in regions where we observe methanol masers, and lowest ratio when we don't see any masers. So this map seems to be quite in agreement with the more sophisticated rotation diagrams. Finally, accounting for the masers, I had an inspiration of the VBD diagrams, but instead of H alpha, oxygen 3, for example, I tried to put in the axis the production of the extraction of methanol in non-LT, a methanol maser driven by shocks. So what I did was to put in the y-axis the shock tracer, like the SIO over HNCO, and in the x-axis the PDL, the photodissociation rate tracer. And for this, I use what I showed you before, the SIO over HNCO, and here CN, that is a molecule people normally use to trace cosmic rays. But if you do this only CN, or only, for example, if you use SIO over HNCO, the region, the central region will not be covered. So, and it hasn't a maser, so should not be there. But if you combine the two and select only this, the number 3, this part of the spaxel, we will see that the methanol masers in this family series are only located in regions with weak shocks and not very high photodissociation. So if I do the flag here, we will see that I only detected methanol masers in regions with weak shocks and a low amount of photodissociation, while here we don't see anything. The explanation is that methanol will be destroyed, so less probability to detect masers. Also, column densities with line ratios are quite in agreement, so there is not a problem using only ratios between moment zero maps. The second method was relative transfer model. They allow us to also fit blending lines that are blended. So I divided again between methanol A and methanol E, and found all this fit all the alchemy spectra in the 10 regions. For methanol E are in blue, for methanol A they are in red. And they are quite in agreement, except some of them that could be in quasi-thermal conditions. But then if we observe the maser lines, they are completely out of the model, like for 3/3 sigma difference. So the synthetic models allow us to compare the theory with the observations in linear scales, not in logarithmic as in the rotation diagrams. I also detected some absorbed and self-absorption for metal, and the synthetic models allow me to detect two other methanol lines. I also did two components for methanol in LTE, and this allowed, here for example in blue is the single component, but if I use a broad component for the line and also a narrow component, the model will follow better the profile of the lines. This is from non-LTE model. The non-LTE is in red, and here you see that this line that is in quasi-thermal conditions is only reproduced by non-LTE conditions, and this line that is a maser even goes beyond that. So these are the conditions from the two component models. I also checked for since methanol are class 1 are produced by shocks, I checked for stellar shocks. But the stars are mostly in the center of this galaxy, and we don't see any masers there. So doing the same approach as Bendo in 2015, but they use recombination lines. I obtained the star formation rate per spaxel, but they are only in the inner region. So the shocks come from mainly X1, X2 interactions that are between the bar and the spiral lamps. So the conclusions of this study was that we detected for the first time methanol masers in MAFEC2, and they are not correlated with the infrared emission. We not detected maser in R220, and we detected many new methanol transitions in an extragalactic object. So these are all the new transitions we detected. So the sample was expanded from 5 to 11 transitions. Now what I am trying to do with this in the present year here in IAG is, for example, all this is a summary of what we have found, and we can simply repeat the process, but what was made in galactic sources, do the same for extragalactic sources. For example, this sulfur ratio could be also measured in another galaxy, since we have the panoramic view. This is, for example, for the Milky Way from Young, and we could think in this being another galaxy, like M51, for example, and try to do the same. The other is what we did in extragalactic objects, do the same for galactic sources. So everything I have here is a ratio of some molecules that will be detected in a galactic source, and check whether those sources follow the same pattern, and also present methanol masers. A line I was very interested during the PhD was this, the 7-160 E-methanol, but unfortunately for NGC2/3 we have very broad lines, about 100 kilometers per second width. So this line falls inside the HNC line. Also due to the water absorption, we have very bad conditions to observe it. So galactic sources will allow to have more chances to detect this line because they have lower line width and higher linear resolutions. So as I said, this line has not been reported so far, and is in the line series that where all of the others have been reported except this one and beyond. Because as you go to higher frequencies, the masers are more difficult to detect. And this is what I did recently. So I detected this line in Karma 7, for example, and also in L1641. So doing the same approach, it is possible to detect this line for the first time, and also this other for the first time. And for the other, the higher frequency line, we also detected the line being out of LTE. So they are also others for the next future. Also doing synthetic spectra for the lines in Calma 7. I only did it for Calma 7. I was able to reproduce the line only out of LTE, but not completely. And at 300 GHz, we have a lower beam, so no mixture with Calma 6. So we also detected the line that is here. Sorry. So here, this is the methanol mixer at high frequency, and the one that was not reported as well. And we did this with Apex. So this is the model. In LTE, all these lines are fully LTE, while the Radix model is not fitting the line, but this is necessary for these lines. Finally, what can also be done with the alchemy data that is now in the archive is to produce an SED fitting occupying this part of the SED, and this can serve to feed the infrared band and also the synchrotron and free emission. And this is another project I am working on with the usage of S+ for some points here in the optical range, BLT in this part, BLT NACO, and Hubble also here, alchemy, and extended very large array in these points here. So this will allow us to obtain spectral energy distribution for the first time at 3 arc seconds. So I am trying to do this almost per region here. And I have this for 10 regions. This is
Questions?
You mentioned at the beginning of your talk
metallicity estimated using molecular lines. I have a curiosity. How do the metallists estimated this way compare this? Yes.
You can use this, for example, this relation.
No, to determine the age. Yeah, okay. But I have another question. How do the metallists that you determine using molecular lines compare with the metallists estimated from the gas, from the atomic gas or ionized gas? Because in general, in the optical is what we use. Yeah. So I think it would be interesting to see how they compare. Because we know already that, for example, the metallists in the gas are larger than the metallists in the stars. Because the stars enrich the gas, I would say. But it would be interesting to see the same with the molecular cloud.
Yeah, I was saying that optical will observe the outer layers, but it will also still be comparable.
Do you know whether there is a direct comparison?
No, in general, I haven't seen like much work in optical and radio together. That's one of the reasons I want to combine the two things. Normally, radio astronomers only talk about radio, the radio regime.
Perfect. Thank you.
Interesting. To what extent, because you have these measurements of maser distribution mostly in the nuclear region, right? So what is the scale and at what extent we can derive, yes, from the maser distribution, the morphology of the ring, of the molecular ring around the nuclear region?
I haven't here the slide, but there are some studies in our Milky Way with the resolution, but they are quite common all along the plane, but mostly in this part is the line limb resonances. The shock, the ones that are produced by shocks are more common. Yeah. But yeah, but we can observe them everywhere, in any part of the galaxy, because class 2, for example, are produced where in the proximity of newborn stars, so we can observe them everywhere in the galaxy. And also in other galaxies, I'm not sure about the 6.7 GHz, but it seems to be detected out of the central molecular zone. I will just need to check this slide. So, yeah, for example, this at 6.7 GHz was detected there, very far away from the center. So laser can be detected everywhere.
You have the two, the rotation and the radiative transfer, and you showed both actually, but I didn't get if they match, in the sense that they could be complementary, but both should match as well.
Yeah, for example, for the rotation diagram, I detected the lines at 132, 229, and 84 GHz, and also the one at 198. No, it's not. But I detected those, and then using the rotation, the radiative transfer, I detected the same. The 84 is far away from the model. You don't see it on the model. The 132, the 100, but we were able to detect also some of extra lines, because here we see them in linear scale, so it's easier. It's a bit easier, but they are in agreement. The 229, the 184, and the 132 GHz, and also the other lines. But we detected more transitions. They are in agreement. Sorry. Yeah. I detected only 4 transitions using the rotation diagrams, but more.
It's very hard to
Yeah.
see
Yeah.
from here.
Yeah. But yeah, only 4 from the rotation diagrams, and then detected 8 from the. Well, this is not laser. It's only absorption. It could be anti-inversion, but I am not sure. Let's say 2 more.
More questions?
There was a slide that you mentioned, and maybe a question when you were talking about the presentation. I'll let you know why. Yeah, that. Yeah. That one. That was second.
This.
Next.
The next.
Yeah, and there is 1060. Yeah, no, yeah, this 84.5 gigahertz.
Yes,
And
this.
there's a question mark. Why is
Oh,
the
well,
question mark?
well, no, I simply because my advisor don't believe in the data reduction of this guy. Yeah.
It's so safer.
Yes, it is, and it's a very interesting source.
Yeah.
Sourcing very high energy astrophysics.
Yeah, my advisor said, okay, but we need another study
It's a puzzle.
to.
Very puzzle.
Yeah. Yeah, this was a nature communication, but my advisor, I think he was the advisor of one. And he said, no, this guy is not reducing very well. Maybe he's producing a line, but it's not there. So, but the problem is that no one else have been published with measuring this line in this galaxy. So another study.
They have seen none in the nuclear region, or
No one had tried to repeat the picture. So, yeah. Only for
Thank you again. O coffee break hoje é lá na sala de recepção do Departamento de Astronomia.
Precisamos assinar, né?
Ah, tá.
De uma coisa que era outra.
Nossa, estou muito tensão no slide. Foi ver aquele.
Tipo, você não coisa grande.
Isso, eu também pensei. Isso, eu pensei. Porque não tinha um negocinho vermelho?
Não, eu muito isso.
É, eu pensei. Uau. Obrigada. Aí eu gostei. Da recepção.
Ah, seria.
Isso, estaria. Olha, eu acho que a gente deixa.